Hello there, Mr. Sutton here, bringing you this Algebra 2 1-3 lesson on modeling with linear functions. In this one, we will be writing equations of linear functions, usually from a graph or a table. We'll also be comparing linear equations to solve some real-life problems, and we'll be figuring out some lines of best fit. As a warm-up on this one, let's see if we can recall some of those formulas you learned in the past for writing equations of a line. So take a moment, pause the video, and see if you can remember what the slope-intercept was, the slope formula, which is different than slope-intercept, and also the point-slope form of a line. All right, let's see how that went. So for slope-intercept, this is the one that people tend to remember long after high school. This is y equals mx plus b. And in terms of what these letters in this mean, the m is our, well actually let's start with b. b is our y-intercept. That's where we begin, you could almost think of it as. The m, that's our slope, and that's how much we move from wherever you began, or how much you have to move to stay on the line. Now to find the slope, there's a few ways you could do it. If you have a graph, you might be able to kind of count how far you're going up over how far you're going over, or you might have to use 2 points with a formula. So here's kind of my basic formula. M, the slope, we could think of that as the rise over the run. How much you're going up over how much you're going over to the right. You could also think of it as the change in y over the change in x. Or if you have 2 points, you could think of it as y2 minus y1 over x2 minus x1. And this is if you have 2 points which we're calling x1, y1 and x2, y2. And it actually doesn't matter what order you subtract these in as long as you're consistent. So if you do y1 here, you need to do x1 down here. Now this slope formula is kind of a good halfway point between these two line formulas, because if you take this slope formula and you just multiply both sides of this by this x2 minus x1 and put it over here with the m, you get something pretty close to this point slope formula, where we have y minus y1 equals m times x minus x1. The m here is still the slope, and this one only requires a single point, x1, y1, whatever point that is, like 2, 3 or something like that. And there's definitely benefits to using one of these or the other. Slope-intercept is super easy to use if you have the y-intercept and the slope, but you don't always have that, so point slope is really nice if you have a single point in a slope. Usually when people get something in point slope, they're going to convert it over to slope-intercept, but it's a good starting point. Now that we've reviewed some of those ways of writing linear equations, we're going to do a real-life problem involving using and writing some of those linear equations. So this graph right here is showing the distance that the asteroid 2019 GC6, that's maybe this thing here, I don't know, travels in x seconds. And our first task, we've got a few tasks here. The first one is to write an equation of the line and then interpret the slope. So pause the video and take a moment to see if you can write the equation of the line based off of this graph. And if you look at the graph here, you can actually read the m and the b right off the graph. So give it a shot. All right, let's see how that went. We'll start with the slope, the m. That's going to be the change in y divided by the change in x. So you could use the whole full-blown slope formula for this and use the point 0, 0 and 6, 21. But, I mean, I think we all know what 21 minus 0 and 6 minus 0 are going to be. We're clearly just going up 21 and over 6. So our slope then is 21 over 6. And if you want, you could reduce that to, let's see here, that would be 3.5 or 3.5. Now we need a little bit more than a slope to write an equation of a line. We also need either a point or specifically, even better, the y-intercept if they're going to give it to us. And it looks like on this graph they did give us the y-intercept. They gave us 0, 0. That is the y-intercept. So we have a b value of 0. So this gives us enough information to use our slope-intercept formula, y equals mx plus b. And we see that we can write this as y equals 3.5 x plus 0, which we don't have to write the invisible 0. So there's this equation. Now they also wanted us to interpret the slope. So what does this slope of 3.5 actually mean in this real-life context? Well, a good way of kind of grappling with this is to understand that since slope is the rise over the run, the y's over the x, that means that in real life, the slope means that we have the units of the y's over the units of the x's. So looking at our units and our y-axis, we've got miles here, and the x-axis we have seconds. So that means that slope is just representing miles per second, or basically the speed of the asteroid. So we could say that our asteroid is traveling at 3.5 miles per second. Now there's a little bit more to this problem. They said here that the asteroid came within 136,000 miles of Earth in April of 2019. Maybe that's why it has this 2019 in it. We want to know about how long it takes to travel that distance. I mean, clearly it didn't hit because, like, we're still here. But if it had, how long would it have taken to go straight to the Earth? So for this one, we can actually use this equation that we wrote, y equals 3.5 times x. This 136,000 is the distance traveled, so that's a y value. We can actually replace this y with 136,000. And then we'll be essentially solving for the x, and that'll tell us how long. Well, to get x, we just have to divide by 3.5. Let me go to my Desmos calculator and do that. So, got my grapher pulled up. We're doing 136,000, no comma needed, divided by 3.5. And that comes out to roughly 38,857.14 seconds. And if you're curious, let's just do answer divided by 60, how many minutes that would be. And let's just do that divided by another 60 to see hours. So it would have taken about 11 hours for it to get to the Earth. I'm just going to put the seconds in there, but we could get it as zoomed out as we want on the time units. So for this next problem, we're going to be comparing some linear models, and you'll see what I'm talking about in a sec. So let's say we have two prom venues charging a rental fee plus a fee per student, and we have a table showing the total cost in dollars for different numbers of students at the Lakeside Inn. So we've got number of students on the left, total cost on the right, and then they're telling us that at the Sunview Resort, the total cost in dollars is given by this equation. They just gave us the equation, y equals 10x plus 600. So we've got two different representations of pricing information. And based on this, we want to know a couple things. One of them is which venue charges less per student, and then how many students must attend for the total cost to be the same. So if we're asking about charge per student, that's going to be the slope, because the charge per student, since the number of students affects the cost, that's how fast this cost is changing as a function of students. So one thing that would be very helpful is if we had possibly two different representations of this Lakeside Inn here. I mean, we've got this nice little table, but if we could get this in equation form, then we could maybe figure out the slopes and compare them. So that would be my tip to you before you pause the video and try this one out, is write an equation for the table-based function and then see if you can put it in slope-intercept and get the slope and compare it to this one. All right, so let's see how that went for you. So one important question I have to ask if I'm going to get a slope out of this table is, are we going up by the same amount? Is this actually a constant slope? So we go up by 25, and it looks like we're going up by 300 when that happens. Going up another 25 brings us up another 300, and that pattern continues. So let me just take the last number minus the first number for the y values. So 2700 minus 1500. And then I'll subtract the last and first x values, so 200 minus 100. So this is going to be 1200 over 100, which comes out to 12. So that's actually $12 per student. Now, I could actually already answer the question since I know the slope of this one, and I could probably quickly find the slope of this other one. But let me just go a little bit further and create an equation out of this, because I'm going to need that for the next part of the problem anyway. Now, if I'm going to write an equation based off this slope, I'm either going to need, again, like I had on the last problem, the y-intercept, or if I don't have that, I'm going to have to use some random point out of here and use point slope. I might be able to figure out the y-intercept if I work backwards, but I feel like it's going to be faster just to use any point out of here. So I'm going to use the point slope then, y minus y1 equals m times x minus x1. And I'm going to do y minus 1500. I'm going to be using this first data entry. My slope is going to be this 12 that I just found, and I have x minus the first x value, 100. And again, I'm going to put this in slope intercept. My job later on is going to be a little easier in that format. So I can distribute this 12. So that gives me 12x minus 1200. And then if I add this 1500 over to the other side, I have y equals 12x plus 300. So we can see out of this that Sunview with a slope of 10 versus the slope of 12 that we found for Lakeview, Sunview is going to charge less per student. That doesn't necessarily mean the overall price is going to be less, because you have to factor in kind of the initial startup fee that both of these are charging. So then that brings us to our next question. Which venue, or how many students must attend for the total cost to be the same? Because I think what's happening here is Sunview, so Lakeview is starting out cheaper, but then eventually that more expensive price per student is going to overtake Sunview. So one way I could figure out when they're breaking even basically is by solving a system of equations. I've got y equals 10x plus 600 and y equals 12x plus 300. So we're basically trying to see if we were to graph these lines out where they would cross. Now I could use Desmos and just figure that out pretty quickly, or if I just want to do this with algebra, I could use the substitution method to see where these lines intersect. In fact, let's see how much you remember about substitution method. If you remember it, pause the video and see if you can solve the system for the x value is what we're looking for. How many students? All right, did you get it? So we can use substitution by replacing this y right here with the stuff that this y up here equals, with this 10x plus 600. So I can write 10x plus 600 equals 12x plus 300. Moving the x's over to the left, that's going to be a negative 2x over there, 10x minus 12x. And subtracting 600 over to the right side, that's negative 300. Dividing by x is going to give me 150, and that's 150 students that we're breaking even at. If you are doing this lesson as part of the Algebra 2 course, then this is the end of part 1 for you. If you're doing it as part of the Algebra 2 honors, then just keep going. All right, if you're doing this as part of the Algebra 2 course, this is the beginning of part 2 for you. Algebra 2 honors, you're just staying on the track here. In a little bit, we are going to be figuring out a line of best fit for a table-defined function, and also talking a bit about the correlation coefficient of that function. Before we do that, we should probably define all of that stuff. So for this, we need actually a more general concept first, called a regression. A regression is a function whose graph comes as close as possible to all the points in a data set. So if I have a bunch of dots on a graph from a data set, and I try to draw either a line, or it could be a parabola, or really any function that you want, you're basically trying to find some shape that gets as close as possible to hitting all these points. And how do you figure out as close as possible to all the points? Well, there's a distance from the curve to each of those points, so you're trying to minimize that combined distance if you were to add all those little distances together. So now when we're talking about a line of best fit, we're talking about a specific type of regression. A linear regression is what the line of best fit is asking about. And you could try to do this by hand. Basically pick 2 points or try to draw your line and then pick 2 points on the line and find the slope and all the other things. But this is typically done using technology, because it is a lot of number crunching as the number of points go up. And one thing that technology can tell us pretty quickly is something called the correlation coefficient. The correlation coefficient, which we denote with an R, not to be confused with radius, is a measure from -1 to 1 of how well a regression fits the points. This regression up here fits these points pretty well, but you can imagine if these points were a little bit more spaced out, then it wouldn't fit quite as well. We wouldn't be able to hit nearly as many of them. So this rating from -1 to 1, here's kind of how this scale works if you're trying to analyze your R value. A -1 would tell us that we had a strong negative correlation. Basically, as the X values go up, the Y values go down, and they're very closely related. As you get closer and closer to 0, that becomes a weaker correlation to the point where at 0 you have no correlation at all. And then as you get more and more positive, you have an increasingly stronger correlation where 1 would be the strongest positive correlation you could have. You're very rarely going to get a -1 or a 1 unless it's a perfect linear function to begin with, but you can usually get pretty close. So with that theoretical understanding of line of best fit in mind, let's take a look at an application of this. The math on this is going to get a little hairy, as it were. We've got this table that talks about months versus hair length. They didn't really go too much more into the backstory on this one, but you can imagine basically measuring how long people's hair grows over a certain number of months. So what do they want us to do with this? Well, they want us to determine whether the data here are showing a linear relationship. And if so, they want us to write the equation of the line of best fit and then estimate y when x equals 15 and explain what that means. Then after all that, find and interpret the correlation coefficient. All right, so let's start with getting the line of best fit and seeing if it even is a linear relationship. For this, we're going to use technology. We're going to use the Desmos grapher, and there's a few instructions that I'm going to go through, and then you can pause the video and try to follow those instructions and see how it goes. So first thing you're going to need to do is to actually plot this data on Desmos. And the way you're going to pull up a table that you can make in Desmos is there's a little plus you're going to see in the upper left. So if you click on that plus, it'll give you the option to add a table. And then you can just fill in these values. This top row here is all your X values, which will be a column in Desmos. And this bottom row here is all your Y values. Just make sure you have the right ones with each other. Once you've got that in there, the next couple things you're going to do, this second step is kind of optional, but still very helpful, and that is to press the Zoom Fit button on there. And that looks like a little magnifying glass with a plus in it. What this is going to do is it's going to give you the perfect window in Desmos so that you can see all of the points you've just graphed at once, which could be very helpful to figuring out how linear this thing looks. Once you've done that, or not done that, your last step, which you are going to need to absolutely do, is going to be to press the regression button, which looks like this line going through these points here. That's a regression button. Now the default setting on this is for a linear regression, so once you press this you'll automatically get exactly what you needed, but there's a drop-down menu where if you wanted to, you could change it to any other function you wanted. So pause the video and give this a shot, and then we'll pull it back together and I'll show you how I did it. All right, let's go on Desmos then. So I've opened up Desmos and I'm on the graphing portion of this. Here's that plus I was talking about, and we're going to choose table. And then let me just enter these points in the table. So I'll just do the X values first. We've got 9, 13, and 18. Whoops. Try that again. 18, 22, 23. And then let me go back up and go to my Y values, which is 3, 5, 7, and 10. That kind of breaks that pattern. And then 11. So now here is this magnifier zoom fit. Let me move everything over now so we can see the whole thing, and then press that. And it zooms out to give us a nice little picture of those points. Now just kind of looking here, this definitely looks pretty linear, but we can know for sure by pressing this regression button, add regression. And there they've drawn a line, trying to hit as many of those as possible. And this is the best any line will ever be because the computer calculated it. So we see here that this linear regression is in the drop-down menu. Again, you could pick a different regression if you wanted. You could try a quadratic, but you'll see it doesn't work out quite as well. So let's go back to linear. And the equation that they were talking about is this y equals 0.556338x minus 2 point all that crazy stuff. So I'm going to go back and first off, I think we can agree that this is a linear relationship or close enough. And there was the equation that we just found. And I truncated it a little bit, so I'm writing the approximately equals. But that is basically the equation that they came up with. Now, one thing they want us to do was to estimate y when x was 15. So I basically would just need to plug in 15 for this x value. And I could plug it in this approximated one, but I would actually like to get the closest value possible. So I'm going to go back to Desmos, and what I'm going to do, I'm going to be a little sneaky. Right here, you can export a snapshot to the expression list here. Basically, take this and paste it down below. And I'm just going to change this y into an f of x so that it's a little easier to plug things into this function. Now if I press enter and just type in f of 15, I don't even need to replace it directly. I can just do it this way, and it gives me about 6.09 and some change. So I'll call it about 6.09. Now, one thing they wanted us to do was to explain the meaning of this in context. So this is an estimated output when the input is 15. Well, the inputs on this are the number of months that your hair has been growing for, and the output is how long your hair is. So this is basically saying after 15 months, your hair is about, we'll call it 6 inches. And the other thing that they wanted us to do, usually they don't ask for all of this stuff at once, but I wanted to kind of cover all our bases with one problem here, is they want to know about this correlation coefficient. So that's that R value. So looking back at Desmos, back up here, we see that there's this an R squared, there's this other residual thing that we're not going to talk about, but then there's this R, and here it equals 0.9905. So I'm going to write that down here, and I'm just going to round it off to 0.99. Now, interpret the correlation coefficient. They're essentially asking how strong is the correlation between months and hair length, and is it a positive or negative correlation? Well, obviously it's positive because it's not negative. And again, the closer you are to 1, the stronger the correlation is. Now, we can hem and haw over, what's a weak versus a strong, like at what exact number does that happen? But I think we can agree at 0.99, you're pretty darn strong. You can't get much better. So this is going to be a strong positive correlation. And honestly, I would say anything over like 0.9 or 0.85 is strong. Anything under that, I guess, is kind of up for debate. So this concludes our lesson on modeling with linear equations. And on the last problem, we managed to hit linear equations and modeling at the same time with this hair problem here. So how about that? Till next time, Mr. Sutton signing off.